Okay. Okay, hey everyone. Sorry, my daughter is in the background. And sorry I'm not there today. I normally would go through this with you in person, but this will make do. Um, in your video notes, you would have learned about types of decay, alpha, beta, and gamma, just briefly, right? There were some tables in the slides that went through each of these processes, but I'm going to give you some examples that will hopefully help. I just kind of threw this together. So sorry about the blurriness up top, but you will see this in your worksheet, so it shouldn't be too foreign to you. When we're doing types of decay, you're also going to want to have the periodic table nearby. I'm not going to split screen or bounce back and forth with my periodic table just to help make things less nauseating on your side of things, but you'll want to have one just so it makes a little more sense. Um, so we're going to start here with alpha decay on the left side here. You can see on my chart, this is very similar to what you saw in your book, but I just wanted to clarify some pieces. So for alpha decay, it's going to involve the loss of a helium particle or a helium atom. We also call it an alpha particle, hence its name, alpha decay. And so it has that, alpha symbol. What happens during this decay process is it's actually losing two protons and losing two neutrons as well. That's what makes up our helium atom. So if you look at the atomic number, we're going to see a change in the element, and that's going to decrease by 2. And because we're losing two protons and two neutrons, that means the mass number is decreasing by 4. So let me give you an example of one, and I'm going to try and write with this pen, so we'll see how this goes. I'm going to use the element. Actually, during these, you're going to see a lot of isotopes because isotopes are radioactive and they're going to want to go through this process of decay. And so this is where the pen has failed me. That's a 2, even though it doesn't really look like it. 241. I'm going to use americium, the isotope americium 241. Okay. When I look on my periodic table, I'm going to see that americium is down towards the bottom in that row of transition metals that's at the very, very bottom. Its atomic number is 95. Okay, so that's what this is. This is atomic number down below. And then up top here is going to be the mass number. And again, these are isotopes. So 241 is not what matches on the periodic table. I'm very aware of that. That's because americium 241 is pretty radioactive. It wants to break down. And we actually find americium 241 in all of our smoke detectors that we have, like in our homes, which is really, really interesting. So it's going to go through this process of alpha decay. And when that happens, it's going to lose those two protons, it's going to lose those two neutrons, and we're going to see it change and stabilize into a different atom. So again, we're going to lose a helium atom in alpha decay. So you're going to see helium involved in the equation. And then we're going to figure out what did it turn into in the end. So we're basically setting this up like an algebraic equation, right? So I'm going to say that this is an equal symbol over here, and everything on my right side over here has to add up to what's on my left side. So as I go through here, I can, work forwards or backwards, however you want to, but I always like to go 95 minus 2 gives me what? Hopefully you're all able to say 93. Bless you, Danica. Um, and then if we lose 4 in our mass number here, 241 minus 4, we should be able to say that leaves us with 2. Oh, it's so terrible, and I apologize. 237 is the new mass number that this americium has changed into. So then I'm going to look at my periodic table to figure out what element I have. And I'm always going to look up the atomic number, the smaller one on there. And when I look on my periodic table, I'm going to say, hey, number 93 on the periodic table is neptunium. So neptunium is my new stabilized atom that's gone through alpha decay. And that americium turned into neptunium once it went through that decay process. Okay? So just some basic calculations. Reminder that the top number is the mass number, the bottom one is the atomic number. And again, the mass numbers are not going to match what's on the periodic table because they're isotopes, which are unstable. Now, another feature of alpha decay is this simple fact of the matter that when they go through alpha decay, they're losing some weight. So this is for our particles that are too heavy in the nucleus, okay? Because we're talking about protons and neutrons, right? So their nucleus is just too heavy. They need to lose some weight in order to stabilize and then get back to normal. So they lose this alpha particle or this helium atom, and then they convert into something new. All right, now we're going to go through beta decay. In beta decay, again, typically this leads to kind of a chain reaction, but it does have to deal with a little instability in its mass again. So we're going to see some changes in protons and neutrons. What's interesting about beta decay here is that we're going to see no change in the overall mass number, but we are going to see a neutron convert into a proton. So that adjustment, we're going to see some changes in atomic number, but an overall no change in its mass. So how do we represent that with a symbol? You might see this letter E. Again, we talked about E's way back in chapter 12 when we talked about elementary charges. It just means something that's really teeny tiny, like our protons and our neutrons. You might also see this beta symbol, the letter B with a long tail. And then this -1 symbol is telling us that the atomic number is actually going to increase by 1. So my example for this one is going to be potassium 40. Potassium 40, like what we see in our wonderful bananas that we eat every single day. Just kidding, I hate bananas. So I do not eat them every day. When we look on our periodic table, we can see that potassium has an atomic number of 19. We know that doesn't change ever for the element, but its mass number up top can change. Like I said before, we're going to use that isotope number 40. Sorry, Danica. When it goes through this process, we're going to see these symbols written. So that's my 0. Sorry, again, I know. That's my -1. Here's my E representing beta decay. When I do this, I am going to go through and do the same algebraic work that I was doing before. 40 minus 0 still is 40. There's no change in the mass for my beta decays, so I'm still going to have 40 over here. But if I have 19 minus -1, that really means I'm adding that 1 to my original atomic number. So this is really saying 19 plus 1. So my new atomic number is going to be 20. Or think about it backwards. What minus 1 gives you 19? Well, 20 minus 1 gives you 19, okay? So when I look up number 20 on my periodic table, I know that my radioactive potassium 40 has now gone through beta decay and has turned into calcium 40, which is crazy. Potassium turns into calcium. Okay, so that's our beta decay. Oh yeah, when I talk about beta decay, I like to think about it like hot lunches in the cafeteria, right? One day you might have chicken patties for lunch. The next day it might be, like a chicken salad. So they take something that you originally have and just tweak it a little bit, but the original piece is still there. So its mass is unchanged, but its atomic number increases by 1. So it's just tweaked a little bit. Our last type of decay in radioactive decay is gamma decay. That's represented by this little symbol, it actually looks like this. Think about it, an upside down fish. And so this one is easy peasy because we're going to see 0 and 0 for our mass and for our atomic number changes. We're going to see no changes across the board. This is like you've had, you know, 2 or 3 cans of Red Bull going into class and you're super energized and you're sitting there and your hand is shaking, your leg is shaking, you can't sit still. This is what happens for gamma decay. It just has really high energy and it has to give off these gamma rays in order to stabilize and relax. So these are going to just shoot off some gamma rays. Now, typically we see gamma radiation also occurring with either beta or alpha. Usually it goes hand in hand, but I'll give you one where it's just all by itself. So we're going to use nickel 60 as our example. 60 is the mass, so I'm writing that up here on top as best as I can. On the periodic table, nickel is element number 28. Not that great, but you got it. And then I'm going to see that there's no changes across the board for nickel 60 other than the fact that it's going to be losing that gamma radiation so that its energy level decreases. And so again, when I do this basic calculation, I'm going to have the exact same atom I had before, right? I'm still going to have 60 minus 0 is 60. 28 minus 0 is still 28. And that means I still have atom number 28, which is element nickel again. So no changes. The only thing that occurred, like I said before, is that it lost some radiation off of it so that its energy is more balanced and stabilized. Okay? So those are our 3 types. I'm just going to jump out of here, get to my radioactive decay worksheet. This is your assignment today. This first page is going to be extra credit. You can read through it. It's a little chain reaction piece where once you figure out your final change, that becomes the beginning of your next reaction, and so on and so forth. So that's easy peasy lemon squeezy. Those of you at home might have to write this in your notebook when you're doing these because these are not fillable on the Google Doc, or you can just insert a little text box and type into it. Okay. The last thing I'm going to do here is talk about an example here on nuclear equations that we see in our assignment. So here's polonium-214 with an atomic number of 84. It's going to go through a nuclear decay process and turn into lead-210. And during that, we need to figure out what happened to it. What type of decay was it? If I do this quick subtraction, 214 minus 210, I have a 4 left over. When I do the bottom and my atomic number, 84 minus 82 is 2. And so when I look up what type of decay or what element this is, right? Element number 2, hopefully that's ringing a bell to our alpha decay type, and that is helium. And you'll just work through each of these just like the previous examples. You can always reverse back and rewind in the video if you want to get a specific example that goes with it. But again, anytime you see these heliums, we've got alpha decay. Anytime you see this -1 with the E, we've got beta decay. And then you can see at the bottom here, there's a couple gamma ray examples. Nothing happens, remember, with gamma. So it's in combination with the other ones. Hopefully that helps. Sorry about my little Danica in the background, but good luck.